Hello everyone. Today I'm going to talk about sparse channel estimation using compress sensing techniques. And this is what I have done for my wireless communication project. First I'll say what exactly is this sparse estimation. This is a kind of regularized estimation. So I'll talk a little about how regularization is done and how that is going to help. Then I will talk about the estimation in the context of channel estimation in wireless communication. Then I'll say a little about what exactly is the OFDM standard and how OFDM is used for various applications, and how OFDM channel estimation can be done under a very sparse context using the same methodologies we have discussed earlier. So first let me start about why should we even be concerned about this problem. Why there is a sparse multipass channel? Let's see, we have a transmit antenna and a receive antenna, and through multiple reflections and scattering we get a very distorted version of the original transmitted signal. Now this distortion is modeled mathematically using a delay tap channel, but in a real world scenario we have only a limited number of reflectors, and with very high bandwidth communication happening nowadays, all those delay taps can be resoluted using a very high resolution. So only few of those delay taps will be actually non-zero or will actually be relevant in causing those distortions. All the rest will be totally zero. I mean, they have no significance at all in the signal that is received by the antenna. So why should we be even concerned about those non-zero taps? Well, in a LTI system, what is called as a linear time invariant system, the channel operates as a convolution operator. You can see the received signal is the input signal convoluted with the channel plus additive noise. Now the noise can be Gaussian. We have considered it to be Gaussian or AWGN noise here in our simulations. This convolution is actually a linear operation, as you can see in the second equation. Now any linear equation, when we can either vectorize it or put it in a matrix form. We'll do it later. First let us see, if we want to estimate the vector h, what should we do exactly? Well, we have a set of training data that is x, the signal itself. So we put different delays of x into one row and we concatenate such rows to form a big matrix called the capital X, and we have a target output, or we have the output which the receiver has received, and we want to find out what this mapping is, the mapping that is caused by the channel vector h. We want to minimize the L2 norm of y minus xh, which is basically the mean square error. Okay, so this optimization problem is basically called the least square problem. Why least square? Because we are trying to minimize the square of the error vector, and this will actually give us a solution for the estimate of h. However, the actual channel might look something like this, as we have shown in the diagram. You see there are about 120 delay taps, but only 4 of them are actually non-zero. All the rest are zeros. Now any least square operation, this is not regularized. This is going to give us definitely an unbiased solution, but some of those non-zero taps, due to the presence of noise, can actually some of those zero taps, due to the presence of noise, can actually give small non-zero values. Now what problem is that going to cause? For that we have to understand something from the statistical learning perspective. Mean square error is basically the square of bias plus variance plus some irreducible error. Now what that means is there is always a trade-off between bias and variance. If an estimate can actually give us a good variance, then maybe it is not having a good bias. So yeah, there is always this trade-off. Now the least square solution is unbiased, but it has a very high variance due to the presence of noise. What we can do is we have some prior knowledge about the channel itself, right? We know that the channel is sparse, only some of the taps are actually non-zero. Now from a Bayesian perspective, when you have some prior knowledge, you should try to include some information into your optimization problem. And that's what we do here. In the least square solution, we try to put a constraint that is the norm, the L1 norm of the channel vector is less than a particular value. Now why this? Well, what we should have done is actually go for L0 norm. L0 norm is basically the number of non-zero entities in a vector. And we could have said like, okay, let the L0 norm of H be less than something, okay? However, what that problem would be is that it won't remain a convex optimization problem anymore. L0 norm is not going to be convex. L1 norm is the closest and sparsest convex approximation of the L0 norm. That's why L1 norm has been popularly used since last 10 to 12 years. And okay, using Lagrangian technique, the least square problem now with a constraint can be converted into an unconstrained optimization problem, which looks like minimize y minus xh norm square plus lambda times the L1 norm of h. Now not only this solution is going to reduce the variance of the estimate, but it's also going to effectively reduce the overall mean square error. We are going to see that later. Okay, now you remember I talked like the linear convolution. Since being a linear operation, we can also vectorize it or put it into a matrix form, and that's what we are going to do here. We are trying to put all the vectors, the input vectors, in the form of a Toeplitz matrix, as can be seen the matrix A, and now the received vector R is going to be just the matrix A times the vector H, the channel vector H, plus again noise put in a vectorized form. When we have such a form like this, I mean when we write the convolution operation as a matrix operation, then all we can do is just apply the same unconstrained optimization problem we saw in the previous slide, that is minimize R minus H whole square plus lambda times H1. Now this is popularly known as the lasso problem, or yeah, so it's a shrinkage version of least square. There are different ways to solve this problem, this L1 penalty problems. One of those ways is quadratic programming. There is also a popular technique which is commonly used nowadays, always in fact, for lasso, that is least angle regression and shrinkage, that was proposed for lasso by Trevor Hasty and Efron and those guys. There is also different other techniques like matching persuade and basis persuade. We are not going to talk about those in details as they are like covered in an optimization course, but we are going to use them in our perspective, that is for sparse channel estimation. What I did first is I used the same equations which I came up with in the last slide into a single source, single carrier. That is just we have simulated random data, we convolve it with a channel, receive it, and then try to estimate the channel using an L1 penalty, and then compare it with the conventional least square solution. And our performance measure is the residual error, that is the mean square error between the channel estimate and the actual channel vector. For different SNRs, we can see that the sparse solution outperforms the least square solution very convincingly. And in fact, the difference is quite prominent in the lower SNR regions. It is quite intuitive and it is quite agreeable too, because in the lower SNR regions you have a very high noise variance, and that is going to significantly mar the zero taps in the channel vector estimate when we are using a least square solution. However, when you are using a sparse solution, they shrink it, or they like use a threshold that totally pushes those zero taps to zero itself, and all the active vectors or all the active taps are recovered perfectly, and all the non-active or the zero taps are pushed to zero. So you are effectively reducing the variance, and this consequently leads to a lower mean square error too. Now we are going to actually apply these techniques to a more real world type communication system rather than just single source single carrier. Well, single source single carriers were used way back. Nowadays multi-carrier and even multiple access and multiple input multiple output systems are used. What exactly is OFDM? Well, I'm pretty sure if you're listening to this video you might be knowing what OFDM is. It's orthogonal frequency domain multiplexing. It's a very popular scheme. It's used in digital television and audio broadcasting, even used in Wi-Fi, WLAN, that is IEEE 802.11, yeah, G and AC, all these standards, in 4G wireless communication for mobile phones. What that does is you actually divide the signal into different subcarriers, and all those subcarriers, even if they are overlapping, but they are still orthogonal to each other. As you can see, for example, just compare the first and the second subcarrier, the brown and the red one. The red one reaches zero exactly where the brown one has its peak, right? Now what we see in this figure, I can actually show you in more details in my project report, where I've clearly shown that all the FFT matrix we have constructed, that is going to be an orthogonal matrix. So each of the two subcarriers, any two subcarriers chosen randomly, are going to be orthogonal to each other. So they can be treated as separate channels itself. Okay, what exactly OFDM system looks like is something like this. Okay, we have an input, we convert it into a serial to parallel converter. Let's say we try to bring out about like n of those bits together. We do a signal mapper. This part is basically the channel coding and the modulation part. In our simulations I used 4QAM, and I didn't use any kind of channel modding, as we are using just a multipath channel and try to compare like how exactly the channel estimation is going. So I just use 4QAM symbols and quadrature amplitude modulation symbols, and after the modulation you try and insert some of the pilots in here. Now why those pilots are inserted? These pilots are inserted so that you can actually track some of the information like carrier frequency offset. You can also use it for phase synchronization and all other kinds of synchronization. Then you actually go for an IFFT. Okay, what this IFFT does eventually is that it uses the very simple trick, that is a convolution operation in time domain. When it is converted using a Fourier transform, it basically leads to just a multiplication operation. Now when you do this IFFT, and in the receiver side you are actually doing also an FFT, you are trying to translate this channel into the frequency domain where it is just plain multiplication. It is way easier to estimate the channel this way. And finally we use an up converter and then send it using a carrier frequency to the channel, and the decoder part is just the opposite of all the blocks we have used in the transmit side. One more part is the cyclic prefix addition. Now what exactly is the cyclic prefix addition? Well, for each OFDM symbol you have got, like for example just after the IFFT operation in the transmit system, we take last TG part of the OFDM symbol and prefix it onto the start of the symbol. Now why this is done is because two of the symbols can actually lead to inter-symbol interference when you are passing through a channel. But if you do the cyclic prefix kind of thing, Well, even if they interfere, and when you receive it, you can actually chunk the CP out, because that is totally redundant. So in this way, you are actually recovering the entire OFDM symbol, and since you have chunked the CP out, you have not lost any information, or you have not added any nuisance to your received signal. Here the channel is going to be a slightly different. Okay, what we did was we actually took a time varying signal. What a time varying signal does is, a channel with a delay profile might also change with time. For example, if you just take one horizontal row over here, that shows one particular channel for different delays. Okay, so it is basically a multipath channel. Now at T0 this was the channel. Let's say after T1, okay, at that point of time those channel tabs might have changed. Now why this is so? Because some of the reflectors might be cars, or some of the reflectors might be an aeroplane or something, and they move, and with that motion your channel and the physical setting of the channel you have, that changes. And also you have your own motion, and the receiver has its own motion. They also add up to Doppler frequency. So considering all this, you actually end up using a multipath channel. We use this multipath channel for our simulations, and we also generated an OFDM, about 100 OFDM symbols, and then sent it through the channel estimator. And we did the same experiment, that is least square channel estimate and sparse channel estimate. In this slide, however, the performance measure that was used was the SNR-BER curve, because that's what we are effectively interested in, right? We need to reduce the bit error rate, or we need to receive as perfect information as possible. Again, as can be seen, for every SNR, the sparse estimate is giving a lower bitrate error as compared to the least square estimate. And yeah, as expected, the graph is giving, for example, if we take like 0.05, we are getting about 4 to 5 dB SNR gain. That's considerable. In this field, lasso and L1 penalty, there has been lots and lots of work, and several methods have come up, and we can use all those methods for different for our purpose specifically, that is fast channel estimation. And yeah, that's all I have to say. Hope you enjoyed this, and thank you very much.